Hello everyone, and welcome to this video on the complex number system. In this video, I'm not going to really do any writing. I've already written a lot of this stuff out. It's just going to be a lesson in number systems, showing you what different number systems look like, maybe some ones we're familiar with, and working our way up to the complex number system. And of course examples of numbers that belong to each number system along the way, and some attributes of each number system along the way. Okay, so my first page, I have, again, just going over some number systems here, and probably some ones you're familiar with. So we have what are called the natural numbers. I've also seen this referred to as the counting numbers in some books, because these are the numbers used to count 1, 2, 3, 4, 5, 6, etc. Just keep going up by 1, but starting at 1. Now in some textbooks I've also seen the number 0 thrown in with the natural numbers, so if you ever come across a textbook where 0 is also considered a natural number, don't worry too much about it. It's not that big a deal. Alright, then in some textbooks, 0 is not considered a natural number, and in those textbooks you have a new set called the whole numbers, which is just the natural numbers 1, 2, 3, 4, 5, 6, 7, etc. with the number 0 added. Right, so the only difference between these two sets is the whole number set has the number 0 in it. Alright, then adding to this, if you were to take the whole numbers and all their opposites, -1, -2, -3, and so on, you get what's called the set of integers. So it's, again, -7, -8, -9, -10, -11 going that way, lower and lower and lower, up to, -3, -2, -1, and then the whole numbers, 0, 1, 2, 3, 4, 5. All of those are considered integers, right? The whole numbers and their opposites, their negatives. Then adding to this set, we have the rational numbers, right? I do have a lot to say about the rational numbers. I've written in set builder notation here where the rational numbers is the set of every number in the rational numbers looks like this, or can look like this, where you have m over n as a ratio, right? Rational ratio, a fraction. Every number in the rational numbers can be written like this, m over n, such that, where m and n, this numerator and denominator, are integers. So one of these guys. And of course, the denominator n is not 0. So I throw some examples here. The number 5, you can write that as m over n, where you have integer over integer, right? You can write 5 as, 5 over 1, or 25 over 5, right? You can write it as a ratio of two integers, two of these. -8, you can write as -8 over 1, or -16 divided by 2. But again, you can write it as a ratio of two of these integers. In fact, you could do that with every integer, right? 5 is an integer, you can just write it as 5 over 1. -8 is an integer, right? You can just write that as -8 over 1. All the integers are rational, right? You can take any one of these and divide it by 1, put it over 1, and consider it a rational number. But there's plenty of other fractions that aren't going to be equal to an integer, right? Like 1 over 2, right? 1/2. That's not an integer, but it is a ratio of two integers, right? Integer 1 over integer 2. -2 over 3, -2/3 is a rational number, integer over integer. Some crazy 124 over -17, integer over integer, and so on. I can make up examples all day long. But it's just any number that can be written as in the form integer over integer, and that denominator integer is not 0. All right, now continuing with this, all right, I'm still talking about the rational numbers here. Something else to say about the rational numbers. Let's take a look at their decimal forms. Right, write them as a decimal. Now, if you take an integer itself, right, like the number 3, that's just 3 point, and then you can add on zeros forever. Right, well, remember the little bar above something means it's repeating. 3.0000000. Now, same thing with negative 8, right? Negative 8 you can write as negative 8 point and then a bunch of zeros forever. Some fractions that aren't integers, like 1/4 is not an integer, but it is rational, right? It's an integer over an integer. When you write that as a decimal, that would be 0.25, and then it would stop. And when a decimal stops or terminates, you can throw zeros on it forever afterwards, and it wouldn't change the value. So I pointed that out here. If a number in decimal form stops somewhere, and you can throw a bunch of zeros at the end, right? Ends in all zeros. That's called a terminating decimal. So negative 8 is a terminating decimal. 3 is a terminating decimal. 1/4 is 1/2, right? 1/2 would be equal to 0.5, and then that's where it stops, and then I could throw zeros on forever. But those are all examples of terminating decimals that actually have an end point before all these zeros. And then there's other kinds of decimals, other kinds of rational numbers that don't have terminating decimals, that don't end in a bunch of zeros forever. Like 1/3, right? Integer over integer. 1/3, that's rational. Now 1/3 as a decimal is 0.3333333, it's 3 forever, or the repeating 3, little bar over the 3 to indicate it's repeating. But that's not terminating. There's no point where it stops and then you can throw a bunch of zeros forever. It's 3 forever. This is another example. Negative 4 integer divided by 11, right? That's a rational number, negative 4/11. When written as a decimal, would be negative 0.3636363636. The bar over the 36, because the 36 is repeating. And again, it wouldn't stop anywhere. And then I add a bunch of zeros. It's going to be 36363636 forever. So these kind of decimals are going to be known, called repeating decimals, hopefully for obvious reasons, right? They have some sort of pattern that repeats forever and ever. The point, 33333, 363636, and so on. So what you're going to notice is that whenever you look at a rational number, if you take an integer divided by another integer, the decimal form of a rational number is going to be either terminating, right? So one of these with where it stops and then you can throw zeros on forever, or it'll be repeating, where it never stops, the repeating pattern never ends, like the 1/3 and negative 4/11 here. But only one of these two. It's going to be one of these, but not both. You can't be both, right? You're either terminating or you are repeating as a decimal when you're talking about rational numbers, right? So every rational number in decimal form is either terminating or repeating. Okay, so let's keep that in mind. All right, and also remember every rational number can be written as an integer over an integer, right? Keep those two things in mind. Because the next set of numbers are that I'm going to talk about are the irrational numbers. Right? Begin with an I there. IR rational. Right? The irrational numbers. Now again, I wrote it in this set builder notation. It's the set of all values that look like this. They're x's, the values of x or whatever letter you want, such that that is a real number. Right? We'll talk about what real numbers are in a second too. Okay, but the values in this set are not rational, right? Irrational, not rational. What does that mean? If I have a number that's not rational, that means it cannot be written as the ratio of two integers, right? It can't be written as 5/7 or 8/-13. It cannot be written like the rational numbers, like a fraction with two integers, an integer in the numerator and denominator. So I have down here some examples of, to start, some famous ones, some famous irrational numbers. The number pi, right? This is that little Greek letter pi, right? Symbol for pi. In decimal form, this is 3.14159, blah, 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 blah. The square root of 2, and really remember we talked about radicals in previous videos. If you take an nth root of a radicand that's not a perfect nth power, it's going to be irrational, the result. So this square root of 2, right, 2 is not a nice perfect square. So the result is irrational, and in decimal form, square root of 2 is 1.414, right? Notice I haven't written any bars here. I'm not talking about any repeating patterns, because you'll see in a second there aren't any. This is another famous one. Now I'm taking this from an intermediate algebra text. Very often you're not seeing the number e for a while, until like maybe pre-calculus or calculus, or maybe late in an intermediate algebra course. But there's this really famous irrational number called e that has a decimal form of 2.71828 and da 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 da. There's another famous one and usually the famous ones are represented by some sort of symbol, right? Like this is another Greek letter here called phi, P-H-I, phi. Sometimes I've heard it said phi, but it's phi. And it's 1.618 da 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 da. This is also referred to as the golden ratio. Right, so this is phi, or the golden ratio. And I'm not going to get into why that is right now, but just know that that symbol is used for these things. And it is an irrational number as well, so it belongs to this set. But then you can make up all sorts of irrational numbers, right? What you're going to notice is, remember what I said earlier about being rational, right? Remember, if you're rational, then your decimal form either terminates or it repeats. But if you're not rational, then you can be neither of these things, right, in decimal form. So the decimal form of an irrational number is neither terminating nor repeating. So these decimal forms I've been writing here with the ellipses at the end, the dot dot dots, will never end, and then you have a bunch of zeros somewhere, and they will never have a repeating pattern that'll keep repeating forever. So these are not like a third or a fourth or anything like that, any rational number. So the decimals never end, they never terminate, and they never have an infinitely repeating pattern. That's crazy, right, to think about. But so they're easy to make up too. All right, here's a couple ones I just made up, while I was writing this out. Here's 0.01, 001, 001, 0001, 00001, and then 5 zeros, then a 1, then 6 zeros, then a 1, and I could do that forever. Just keep increasing the number of zeros between the ones, and you get an irrational number, right? Because again, this would never end, and it's also not 0 1 0 1 0 1 0 1. You're not seeing the same digits over and over and over again in a repeating pattern. So the way I've constructed that number is irrational. There's another one, negative 5 point, and pretty similar to this one, 1 2 3 0, 1 2 3 0 0, 1 2 3 0 0 0, and then 1 2 3 and 4 zeros, 1 2 3 and 5 zeros. I mean, I can describe the number, how it's going to be made, but it is definitely never ending, not terminating, and it's not a repeating pattern. Yeah, you're seeing 1 2 3 1 2 3 1 2 3, but they're split up by these zeros. I'm not seeing 1 2 3 0, 1 2 3 0, 1 2 3 0, 1 2 3 0. It's not the same digits over and over and over again in a repeating, infinitely repeating pattern. So again, irrational. All right. So some interesting numbers, and so we got the rationals that can be written as a ratio of two integers, can be written as a fraction. Their decimals either end or they repeat. Then we have the irrationals, whose decimals never end and never repeat. and they can't be written as a fraction, right? A ratio of two integers. All right, now putting those two sets together, we get the set of the real numbers, right? You heard me mention the real numbers earlier, and I've also mentioned real numbers in plenty of other videos before too. The real numbers are made up of the rational numbers, in union with, I hopefully remember this symbol from a previous video as well. This is the in union with, the union symbol. The irrational numbers. So all the rational numbers are considered real numbers, all the fractions, ratios of integers. Additionally, or all the irrational numbers are also considered real numbers. Right? So every number I've written so far up in this video up to this point is called a real number. Right? And real numbers are usually represented by a number line, right, where each point on the line represents a particular number, a particular real number. So here I have a number line here for you, where usually 0 is marked off at some point to separate positives from negatives. And remember, if you have a number that's to the left of another number, the number on the left side is considered smaller, right, has a smaller value. And I marked off some numbers here. There's a point representing 1, then 2, then 3, and pi, which is a little bigger than 3, e, which is between 2 and 3, closer to 3, square root of 2 is a point, between 1 and 2 there. There's a half. There's that 0.010010001 number I had on the previous page, right a little bit bigger than 0 there. Negative 2/3, negative 1, negative 2, negative e, right? That's about negative 2.71828, negative 3, and so on. And, every single point, no matter where you put a dot here, dot here, dot here. Pick any point on the line, and it represents either a rational number or an irrational number. Right? It represents some real number. Right? Now, one interesting thing to point out, and it's going to be key to the discussing the next set of numbers after this, is that the square of every real number is non-negative, right? When you take a real number and square it, raise it to the second power, multiply it by itself, your result is not negative. For instance, 3 is real. Squared is, positive 9, not negative. Negative 4 is real. When I square it, that's, negative 4 times negative 4, that's positive 16. Again, not negative. 0 is real. When you square it, 0 times 0 is 0, which is, again, not negative. The square root of 2 is real, right? That's irrational, so it's real. When I square it, that's positive 2, not negative. Negative 3/5 is rational, right? Integer over integer. That's a real number. When I square it, negative 3/5 times negative 3/5 would be positive 9/25, not negative, and so on. And I could do this all day long. But if you take any number on the number line, any real number, take any rational number, any irrational number, and raise it to the second power, multiply it by itself, the result is not negative. All right, that is key to remember for the discussion of this next set of numbers. All right, so far we've talked about all the numbers I've written. Every single number I've written so far can be considered a real number, right? And their square is not negative. But what about the numbers out there whose square is not positive? We haven't seen any of those. And so what I'm going to get into on the next page is a totally different set of numbers. Okay, these are not real, and I'll write that. I haven't written that here. I'll write that here. These are called the pure imaginary, or just the imaginary numbers. And over here I have how they're constructed. Set builder notation. It's every single one of these numbers, these pure imaginary numbers, looks like this, where you have b times I, b times I, and the b, the coefficient of the I, is a real number. Right? But these numbers themselves, right, we're in the realm of not real numbers anymore. All right, the whole set is made up of not real numbers. That's the word imaginary is used, right? That doesn't mean they don't exist. Okay, I'm writing them. They're real. They exist. They're not considered, real numbers with my little air quotes, that you can't see. But, again, I don't really care for the fact that they called them real and imaginary. But can't change history. All right. Okay, so these pure imaginary numbers look like, again, this some real number times I. Now, what is this I that I write here, this symbol I? So I have a little definition of that here for you. When you see this symbol I, right, I is the symbol for the square root of -1. So I is the number that when you square it, you get -1. You get a non-positive result. Right? Remember on the last page I mentioned, when you square a real number, it's not negative. This is representing a number that when you square it, it's not positive. Right? Now they might also symbolize it this way. Instead of the letter I, you could see the square root of -1, right? Remember we mentioned this in a video a while back, right? The square root of a negative, even roots of a negative number is again not real. It's one of these pure imaginary numbers. It has a name too. The letter I, this symbol I for the square root of -1 is called the imaginary unit. Right? And I put in this little box here something very important. As I mentioned, it's the square root of -1. So that means if I take this number I, right, this symbol I, and square it, I times I, or the square root of -1 times the square root of -1, that's giving me -1, right? It's a number that when squared is not positive. All right, so I is not considered real. It's one of these, again, pure imaginaries. All right, so some examples down here of some pure imaginaries. Again, they all look like this. There's some real number times this I, right? Some real number times the square root of -1. So 3 times I, right? 3 is real times this I, 3 times I, that's considered pure imaginary. Square root of 2 times I. Now notice how I didn't make the square root very long, right? The I is not inside the square root. So very often, instead of writing it this way, where I have a real number, square root of 2 times I, they'll do it like with variables. They'll put the variable in front, say it's I times the square root of 2, right? Instead of the square root of 2 times I. They mean the same thing though. Here's another example. 1/2 times I, right? A real number times I. So this is, again, purely imaginary. Another way to write this too is, just like with variables, half of x would be x over 2. Half of I can also be written as I over 2, right? But still has this I attached to it. I attached to a real number, so again, purely imaginary, a pure imaginary number. -4 times I, real times I, pure imaginary. Okay, and again, I could make up examples like this all day long, but I will not. All right, and as mentioned out loud, I have it written on the next page. I'm still talking about the pure imaginary numbers here. All right, those numbers that are, b times I, a real number b times this imaginary unit I. So still talking about the pure imaginary numbers here. Remember how for real numbers, the square of a real number was non-negative, not negative. The squares of these pure imaginary numbers are not positive. All right? They're not non-positive real numbers as results. So for example, 2i, right? That's one of these pure imaginaries, right? It's a real number times I. 2i, when I square it, and you can treat I like a variable sometimes, even though it is not, right? Because it's not like x or y or whatever. It actually means something. I is the square root of -1. But you can treat I like a variable in a lot of cases. And so when I take 2i times 2i, that's 4 times I squared, 4i squared. But remember what I said in the previous page, right? I is that number that when squared gives me -1. So when I take 2i times 2i, I get 4i squared. But what's 4 times I squared? That's the same thing as 4 times negative 1, and that is negative 4. See, I end up with a non-positive real number. Right? Negative 4 is real, but it's not positive. So take a pure imaginary and square it. You get a non-positive real number. Now, going through this statement here, saying that the number 2i squared is negative 4 is another way of saying that 2i is a square root of negative 4, right? 2i is a square root of negative 4. All right, remember this symbol meant the principal square root, so if you double check, you can see that if I took negative 2i times negative 2i, that would also be negative 4. But as we've mentioned loads of times now, when you see this symbol, you're asked for what's called the principal square root, the principal root. So usually have the non-negative one, right? So yes, negative 2i to the second power would also be negative 4, but again, you see this symbol, they want the non-negative one, right? Just like always. So 2i is the square root of negative 4. Here's another pure imaginary, right? 3 times I, real times I. When I square that, that's 9i squared. But remember, I squared is negative 1. 9 times negative 1 is negative 9. So what we're seeing here in the second line is that take this pure imaginary 3i and square it, and the result is a non-positive real number, right? Negative 9 is not positive. And if you look at the line in total, right, 3i to the second power is negative 9. That means that 3i is, a square root. In fact, it's the principal square root of negative 9. So you could write this as well. 3i is the square root of negative 9. And then one last example here on this page. Here's another pure imaginary, square root of 2 times I, real times I. When I square that, well, remember the square root of 2 times the square root of 2 is just 2, right? The square root of 4. Real numbers you can use that product rule for, just real numbers though. Then I times I is I squared, and then what is 2 times I squared? Well, remember I squared is negative 1, and then 2 times negative 1 is negative 2. Okay, so this square root of 2 times I, or I times the square root of 2, when I square that, I get negative 2, meaning that this, root 2 times I is a square root of negative 2, right? The principal square root of negative 2. So square root of 2 times I is square root of negative 2. And in fact, you can, and I put this in a bubble down here, this is very important. I'll bring this back up in the next video I make as well. But when you see the square root of a negative number, if I ask what's the principal square root, right? And again, remember this means the principal or the non-negative square root. What's the non-negative or principal square root of negative n, where n is non-negative, right? So this is a negative number in here, right? Like the square root of negative 2 or the square root of negative 9 or the square root of negative 4. When you see that, the square root of negative n, you can rewrite it using this imaginary unit as the square root of n times I, right? And so you can write the square root of a negative number as one of these pure imaginary numbers, right? The square root of n, where n is non-negative, so this is a real number, right? The square root of n, the square root of a non-negative, a real number times I. Or if you'd like, put the I first, I times the square root of n. But keep this in mind. I'm going to again bring this up in a future video. This is very important. When you see the square root of a negative, rewrite it as a pure imaginary, right? Some real number times I, please. All right, so we've seen the real numbers whose squares are not negative. We've seen the pure imaginary numbers whose squares are not positive. Now we finally come to the title of the video, the set of complex numbers. All right. So again, I have it in set builder notation where you have, here's what every single one of these looks like. So what is a complex number? Right? Every complex number looks like this, where you have a plus b times I. That I, again, that's that square root of -1. Right? That's what the I is. Where a and b are real numbers. Right? So you have a real number plus, and then a real number times I. So you have a real number plus a pure imaginary number. Right? So any number that can be written as a real number plus a pure imaginary number is called a complex number. So what we're going to see here in a second is that really in your intermediate algebra texts, even on calculus texts, every number that we see, I should say Calc 1, Calc 2. You'll get into like quaternions and stuff like that. Forget Calc 3. All right, but anyway, any number that we see, any number that we've seen so far, everything is a complex number. And the number a here, I should have written this out, but when you see a plus bi, the number a, the number that doesn't have I attached, that's sometimes referred to as the real part of the number. And the number b, right, that's actually attached to the I. The number b is sometimes referred to as the imaginary part of the number. All right, sorry, I should have had more space for that. All right, so here are some examples. All right, following this down. The number 3. 3, right, I can write 3 as 3 plus, 0 times I. Remember, anything times 0 is 0. So if I add 0i, that really isn't adding anything, and I still have the number 3. But you see how it's written in this a plus bi form, where I have a real number plus another real number times I. So I started off with a real number, and I wrote it in this, a plus bi form. How about negative square root of 2? That's also real. I can write that as negative square root of 2, again, plus 0 times I, which is a 0. So do you see how every real number can be written this way, where you just take the real number and add 0i, and you're in this form up here, this a plus bi. So every real number is a complex number. Can be written like that. So every real number is complex, and so is every pure imaginary, right? Like take just I itself, the number I, that square root of -1. Just pop a 0 in front of that, right? I is equal to 0 plus I, or 0 plus 1i. There's your a plus bi. Real number plus real number times I, real number plus pure imaginary. And you see how this pure imaginary is also complex. Same thing for another. Here's another pure imaginary, -2 times I. That's just, again, throw 0 in front of it. That's equal to 0 plus -2 times I, or 0 minus 2i. It's complex. So not only is every real number a complex number, but every one of those pure imaginary numbers is also considered complex, can be written in that form. And of course there are plenty of others, right? So not just the reals and not just the pure imaginaries, but really any combination of the two. Like here's a real number plus a pure imaginary, 1 plus 3i. That's complex. That takes on that form. Pi, plus -1/2 times I, or pi minus 1/2 times I. That again takes on real number plus pure imaginary number. That takes on this form. 3/5 plus, the square root of 3 times I, or I times the square root of 3. Again, real number plus pure imaginary takes on this form. It is complex. And I could, again, make up examples all day long. But there's loads of them out there, right? Infinitely many examples of complex numbers. Everything you can think of right now in this intermediate algebra, up to pre-calc, calc 1, calc 2. In this context, everything you can think of right now, every number is complex, can be written in this a plus bi form where a and b are real. So this real number a plus, pure imaginary bi, this form is called the standard form of a complex number. And as I mentioned before, the number a, sometimes referred to as the real part of the number, and the number b that's attached to the I is called the imaginary part. All right. So that was a lot, I know. And I have one last page here for you. Just a little diagram. It's not really good looking. It's just a bunch of blobs, but kind of a Venn diagram where each shape represents a different set. Okay, so imagine this giant blob represents all complex numbers, right? All those numbers that are in that a plus bi form. Well, inside that set, we have the set of real numbers, right? So this big oval shape, big pill shape thing here. All these are the real numbers, the numbers whose squares are not negative. And the real numbers is broken up. Notice I got a little divider in here. The real numbers are broken up into the ones that are rational, right? Can be written as a fraction. So these are your your natural numbers, your whole numbers, your integers, and any ratio of two integers are all in here. Their decimals either terminate or repeat. And the other part of the rational numbers are the irrational numbers, right? And these are the numbers that can't be written as a fraction of integers, a ratio of two integers. Their decimals never end and never repeat. All right. But again, all these numbers here in this blob, all the real numbers, when you square them, the result is a non-negative real number. And then a separate blob, a separate set inside the complex numbers still, is the pure imaginaries, right? Those bi, right? The 3i, 2i, negative 1i. Or again, remember that I is the square root of negative 1. I squared would be negative 1. These are numbers that, when you square them, the result is a non-positive real number. And then notice how much blank space there is, because again, there are lots of numbers. There are lots of complex numbers that are not just real or just purely imaginary, but a combination of both. Like I had on the previous page, 1 plus 3i, 2 minus 1/5 I, the square root of 3 plus 9i. There are lots of complex numbers that are not just real or just purely imaginary, but a combination of the two. Right. Okay, so again, pretty long one, a little long discussion. I didn't really have examples where I was working anything out. I did a lot of examples of each kind of number, though. I hope that helped them make sense. And hopefully remember the properties that are very important for real numbers, right? The real numbers squares are non-negative. The pure imaginaries, those numbers squares are non-positive. And what it means to be rational, what it means to be irrational, lots of things to keep in mind throughout this video. And as we go into future videos, when I mention a specific kind of number, I'll be hoping that you've seen this video and know exactly what I'm talking about. All right. And as I like to say at the end of these videos, do the best you can, try the best you can to learn the material on your own before you go looking for help. I have found that people who take the time and the effort to learn something on their own remember those things for longer and remember them better, and I'm more proud of it. So of course, read the material, right? Read through the author's examples, perhaps even try to work out solutions to an author's examples, before you look at how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously, do tons of exercises, practice problems, look up solutions to those whenever they're made available. Check yourself, keep track of your progress. And don't just give up on a problem after one attempt. Very often in mathematics, there are several approaches that'll work for any particular problem. So, if after several attempts at a problem you're still not getting it, perhaps you should read the material again. Maybe even a third time, more slowly, more deliberately. Take good notes. Because if you've been working on some problems there's a good chance you have a better idea, a better grasp as to what the author wants from you, what the author expects of you. So then when you go and read the material again, or that third time, um, you'll know better what to look out for in the reading, or some things might pop out at you that didn't the first time through, and it'll make working on those problems that much easier. But if after that, if after several attempts at problems and several read-throughs of the material, you're still not understanding things, still not getting it, it's not a sign of weakness whatsoever to go out asking for help, go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone who's in your class, who knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online. There's tons of those too. Videos like this one, or plenty of other ones out there better than these. I assure you they're out there and they're easy to find. Just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest thing, is believe in yourself. Try to stay positive about the subject. Maybe even have fun with it. Make it a game. Staying positive when you're struggling and failing at things is very difficult. I understand that. But if you can keep at it, and keep a strong belief in yourself, you'd be amazed at the difference it'll make in the learning experience. And those moments of struggle, those moments of failure, those are the moments when you can learn the most. Right? If you can figure out how to fix things, how to learn from your mistakes, it's gonna be entrenched in your brain, that material, even more so than if you got it on the first try, because you cared more. Right? It's all about it's all about your mindset, the state of mind that you're in. So just stay persistent, keep practicing. Don't give up, and stay positive. Stay positive, please. I just know you'll eventually get it. And thank you very much for watching.